Here we're going to take a look at reduction reactions of aldehydes and ketones. Reduction is often abbreviated by an H in brackets, and in organic chemistry, reductions are, in a simple sense, classified by the increase in number of CH bonds and or a decrease in the number of CO bonds. So that's what we're going to do when we reduce aldehydes and ketones. We're going to be reducing these to alcohols, in which case the CO bond will become a single bond and we'll add a carbon-hydrogen bond to that. There's a couple of common reagents for reduction that we use. The first is sodium borohydride, NaBH4. And if I draw this structure out, let's split it up into the cation sodium plus and the anion BH4 minus. So we have a boron with 4 hydrogen. And that boron bears a negative charge. LiAlH4 is the other reagent. This one is called lithium aluminum hydride. It's often abbreviated as LAH. And this one's very similar in that you have a lithium cation and an aluminum with 4 hydrides attached. And that's our anion. Now both the boron and aluminum really don't want that extra bond, so they can donate a hydride, meaning the 2 electrons between the B and the H, or the Al and the H, can leave the metal and go on to the hydrogen as a lone pair. So what these effectively are sources of hydride H-. So it's the opposite of a proton where you have H+ and no electrons. A hydride is a hydrogen with 2 electrons. Between the two reagents, we find that sodium borohydride is a bit weaker and LAH is a bit stronger. So we're going to find later on that there are things that LAH can do in terms of reduction that sodium borohydride can't. Now, if we're working with aldehydes and ketones, you can use these two reagents interchangeably as the reducing reagent. Both will reduce an aldehyde or a ketone. So here's a couple of examples. And in this first one, we have a ketone. And the reagent that's being added is lithium aluminum hydride. When you see that, just go ahead and simplify it as H-. So let's go through the mechanism to get to the product. When we add H-, that hydride acts as a nucleophile and adds to the carbonyl carbon, and then that will push a pair of electrons up onto the oxygen. Right, at this point, we have this negatively charged oxygen, and we're kind of stuck here. So that's why you see a second step where we add dilute acid. And what the dilute acid does is it just protonates that oxygen. Okay, in the product, I'm not going to draw the hydrogen in, but be aware that it is there. So here we have reduced the carbonyl to an alcohol. This intermediate along the reaction pathway where you have the negative charge on the oxygen, this is known as a tetrahedral intermediate. And we're going to be seeing this intermediate throughout the various reactions that we talk about in this chapter. The second example uses sodium borohydride and methanol. Methanol is the proton source. The one difference here is that because sodium borohydride is a weaker reagent, you can actually mix it with the proton source. So here in this example, we're going to take the starting material and add a hydride to the carbonyl. So just to draw the product, I'm just going to keep everything the same. I'm even going to draw this hydrogen in. Then our double bond O becomes an OH. And you don't have to draw the new hydrogen in, but the new hydrogen was added to that carbon. So there's the product, which is an alcohol. When I showed you the reaction using LAH before, you'll notice that it was a two-step process. You add the lithium aluminum hydride, and then you add water or an acid. That's because lithium aluminum hydride can't be mixed with protic groups, things like water, alcohols, or acids. Let me show you what happens if you try to mix LAH with a proton source. Here's a case of lithium aluminum hydride and water. So the hydride on the LAH is so reactive, what this will do is it'll take its 2 electrons and come over and take a proton from water. So what do we get from that? Well, the 2 hydrogen combine to form hydrogen gas. Then you end up with AlH3 plus hydroxide. Actually, lithium hydroxide. On first glance, this may not seem so bad, but there's something else that's generated with this reaction. You get a lot of heat, and that in combination with the hydrogen gas, organic solvents, and oxygen in the air can lead to a quick lab fire. So it's important to be really careful when working with lithium aluminum hydride.